VSEPR theory. VSEPR theory, remember, stands for valence, shell, electron, pair, repulsion, theory. And the idea is that when molecules form, the electron clouds would like to orient themselves in such a way as to maximize the distance between them. They really do not want to overlap. So in intro, I know we had a chart that showed shapes of molecules, and that's what we're going to remember. Remember, we asked ourselves this question: how many atoms are around the central atom? Now, your book and other books talk about bonding pairs and non-bonding pairs or shared pairs, things like that. But our focus has really been about atoms attached. And when we did that, remember we had, as is a quick review, one atom around the center would be linear. Two atoms around the center, you have a choice of linear or bent. Of course, that has a lone pair. Three atoms around the center, it's either trigonal, planar, or pyramidal, that has the lone pair, or four atoms around the center, and that was tetrahedral. And this is the arrangement of electron pairs around the atom yielding minimum repulsions, so that these electrons are as far apart as possible. But sometimes we have what's called an expanded octet, and that's what we're going to be focusing on in this discussion. The VSEPR theory, but specifically about expanded octet. And this is when you have either five, or six things attached to the central atom, or things around it. Now, as you will see, we did a little bit of this in intro. And I know when with 5 around the center, for example, we might have had PCl5. And when we do the dash diagram for that, we notice that we get something like this. There's a chlorine, there's 5 chlorines attached to the phosphorus being in the center. And you will notice that phosphorus normally has 5 valence electrons. And phosphorus could be, let's say, I'm going to call this the S sublevel. And then the P sublevel, like that. Now normally you could see 3 places where something could bond with phosphorus. Essentially here, here, here. But what happens is P, phosphorus that is, promotes one of its S electrons up to the D sublevel, so that you have one thing in the S, 3 electrons in the P, and 1 electron in the D. So now you have 5 places that can be attached by other atoms. In this case, chlorine can come in and occupy those spaces in the orbitals, so that 6 things can happen around phosphorus as a central atom. Remember, we call this an expanded octet because it can hold greater than 8 electrons around it. It can hold 10, because each line numbers with 2 and there's 5 lines, so there's 10 electrons. And sometimes you will see this as an sp3d hybrid. That's a name for the situation where there's an electron in the S, 3 electrons in the P, and 1 in the D. There are 5 places that these other atoms can attach to phosphorus as the center. And the name, remember, is trigonal bipyramidal. I know we had that intro, as well as octahedral, something like SF6. This is octahedral. And what happens is sulfur's 6 valence electrons are promoted such that there are 6 empty electrons, and that allows for 6 things to bond around sulfur, and that's called an octahedral shape. You can look at these pictures in your textbook, but it could be drawn as well. I know we talked about this in class already. So my focus in this discussion is really to get you to understand new shapes, shapes you haven't seen before. So let's go back to structures that have 5, something that is built around 5 electron pairs around the central atom. Now, if all of the places are occupied by atoms, you have PCl5, which is what we have here. But what if they aren't occupied? What if we have something like this, SF4? All right, so using what we know about dash diagrams, we're going to go to the periodic table, and sulfur has 6 valence electrons, and fluorine has 7. 7 times 4 is 28, and the total when you add them up is 34 dots, and you're going to divide that by 2. That's 17 dashes. So sulfur is going to be in the middle, and we're going to put 4 things around it. Kind of looks like it wants to be tetrahedral-ish. So we have 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, and then we have number 17. Where do we put it? We actually put it on sulfur. In other words, it looks like PCl5, because that's the one up here. And in fact, if I draw PCl5, I'm going to attempt my 3-dimensional drawing, which could be kind of interesting. Think of this as a triangle, almost like, a tortilla chip, something like a Dorito, with a toothpick through it. So you have these 3 things around a triangle, the 2 chlorines being on the edge, another atom in the middle, and then the chlorine on the top and the bottom of the Dorito, if you will. So we have this shape. Now, SF4 is a lot like this, but one of the chlorines has been taken away, and now there's a lone pair there. So it kind of looks like a line. Here's my great drawing for it, with 2 things off of it, and then this is the lone pair. Almost like somebody came along and ripped one off. Now if you were to rotate it and put it down, it would kind of look like a seesaw. You know, a seesaw is that device where people sit on it, right? There we go. Look at that drawing. Looks just like a seesaw. And people, of course, go up and down. And wouldn't you know that this is called seesaw shape? I know you thought I made that up. SF4. This is seesaw shape. Because again, this is kind of the flat part, and this is the part that would go on the ground. So if you rotated this 90 degrees, it would look kind of like this picture right here without the people. And that's a seesaw shape. So SF4 is an example of something that has actually 4 things around the center, but you notice there are 5 things attached to sulfur. 1, 2, 3, 4. And for this argument with the expanded octet, we're including the lone pair as something attached, and therefore it has 5 attached things to the central atom. So that's seesaw shaped. All right. Now I'm going to continue on, and I'm going to erase this so I don't have to scroll down too much, because I'd like you to have this in view. Another expanded octet would be ClF3. All right, again using our Lewis diagrams. Chlorine has 7, as does fluorine. So 4 sometimes 4 is 28 dots, or 14 dashes. So chlorine's going to be in the middle, and there's going to be 1, 2, 3 things around it. All right, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Now, notice I start out like it's going to be full and complete, not an expanded octet. But in this case, I have 12 and I need 2 more. The only thing I can do is add them to the central atom. So there are 5 things. It looks as if there are 5 things attached to the central atom. And so what we have here, I'll take this picture and erase one of these and attach a lone pair to it. And what you will notice happens, of course this is my 3-dimensional looking picture. It actually is like a line, and this is 90 degree. This is a 90-degree angle right here, and this is a 180. So this one, or CLF3, is called T-shaped. So if you turn it to the side, it looks like the letter T. And then also with 5 things occupying around the central atom, some being lone pairs. An example would be I3, negative. So 3 iodines. Obviously iodine again has 7, so that's 21 plus 1, because that's for this -1. So that's 22 or 11 dashes. So I'm going to put the 3 I's in a row. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Okay, so that there are 5 things around iodine. Notice there's only 2 things occupied by bonding pairs. And it's just like if I took this one off, my original picture, and I attached another set of lone pairs there. I3, negative. Also notice, don't forget, if something is an ion, we put it in a square bracket with the charge outside. So I3 would be linear, because those atoms are as far apart as possible, 180 degrees. Excuse me. So that's what's true about things that are expanded octet that have 5 things around the center. Some of them are lone pairs. So we act, the question, how many atoms are around the central atom, the question changes a bit when we're talking about expanded octets. Okay, off of 6, there's 2 other shapes that one could have. Let's look at an example. BRF5. Now, both bromine and fluorine have 7 valence electrons. 6 times 7 is 42 dots, or 21 dashes. Took me a minute. And bromine's in the middle. And we need 5 things around it. 1, 2, 3, 4, 5. So that's 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. And number 21 goes off bromine. Notice there are 6 things centered around bromine. That's why it's under the expanded octet of 6. It's BRF5. Now, here's my attempt at drawing this one. I'm going to do this up where I drew these other pictures. There's no seesaw here, so I'm going to get rid of that. I'll also erase the word expanded octet. Alright, so what does SF6 look like? Well, S, and I'll just make it look generic. There's sulfur, and the 4 F's kind of are like a square. Think of a square piece of paper, almost like a note card, a post-it note, if you will, with something in the middle. An atom in the middle, and something up and down. Almost like if you took a post-it note and stabbed it with a pencil. The top and the bottom of the pencil would be the locations of other atoms, the center would be, and the 4 corners of the post-it note. Kind of looks like that. That's SF6. Now, excuse me, in this case, BRF5 has an extra lone pair. So in other words, what would it be like? Well, it'd be like if I took off this bottom one, and it looked kind of like a pyramid, a square pyramid. Do you see what I mean? Kind of like that in my perfect drawing. Here's one, here's one, here's one, here's one. There's an atom down here, and there's an atom up here. So there's no bottom. There's a lone pair down there. And wouldn't you happen to know, it's called a square pyramid. That's the shape of that. Now, the last one off of that, based on that, would be XEF4. Now, you might be very surprised to know that xenon can form compounds. These noble gases, especially the larger ones, can have expanded octet notations, like this one, xenon and 4 fluorines. So for this one, xenon has 8 electrons, and fluorine has 7 times 4, which is 28. 8 or 6, so 36, 18 dashes. All right, so xenon would be in the middle, and we need 4 things around it. Again, it's kind of looking tetrahedral-esque. So there's 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, and we need 2 more. 17, 18. I'll just put them anywhere around xenon. Notice there are 1, 2, 3, 4, 5, 6 dashes and lines, if you will, off xenon. That's why it comes off number 6, XEF4. Back to my lovely picture here. If I had XEF4, it'd be like I was, whoa there, taking the other atom off there, and in my picture, I'd have something in the middle, and I'd have this, and I'd have this, and I'd have this, and I'd have this, and it would just be kind of square and flat, almost like the Post-it note with no pencil through it, and it's called square planar. And those are the different shapes that you might see depending on how those atoms are oriented. I'm going to show you this, which I found, which I thought was very interesting. You can see the URL up at the top. It's chemed.chem.purdue.edu, and this is the general chem course, so see, if you go into Purdue, you're already a step ahead. This just gives a little bit of an overview. They talk about bonding and non-bonding sites and all that kind of stuff, but in general, this could be helpful for you. They talk about linear, trigonal planar bent, tetrahedral, pyramidal, and the ones I wanted to look at were these. These are the expanded octets. They do a little bit better job of drawing the picture. Here's PF5. That's the trigonal bipyramidal. Here's the SF4. Notice the lone pair over there, and that's the seesaw shaped. Here's with 2 lone pairs on the middle, T-shaped, and 3 lone pairs, linear. 6 atoms around the center, or 6 things around the center, I should say. SF6, BRF5, you notice we take 1 off, and then if we take 2 off, these remain as square planar. So hopefully this will help you as you try to do your Lewis diagrams, add your shape. You do also need to know the bond angles, and you can find the bond angles in the textbook to figure out how far those atoms are away from each other.